Hello again, everyone, and welcome. And we have made it finally to chapter 5.4. This is the last section for Algebra 1, and this, of course, is exponential and logarithmic equations. Now, in the last section at the very end, we actually basically did what this whole section is going to be about. And I want to start off kind of slow. So these are going to be a little more simple examples, but we can actually handle them in different ways. So instead of handling them the usual way, I'll still do that, but I'll show you a different way, maybe not better, but a different way of doing it. And then afterwards, I'm going to summarize what we have learned from this and try to build some strategy for solving these types of equations. And then we'll handle kind of harder ones, actually. So here you may think, well, we can write 16 as 4 to the 2, and then using the one-to-one property of exponents, you just say x is equal to 2, and that's it. And it's the only x value that'll make 4 to some power be 16. So it's kind of, like I said, it's more simple type of example. But there it is. Is there another way of doing this? Totally. There's another way of doing this. If you wanted to use log, you can actually take log base, well, the base is 4. So if you take log base 4 on both sides, you get log base 4 of 4x is equal to 16. You can use the power rule of logarithms to bring the x out. So this is x times log base 4 of 4. But remember, what's log base 4 of 4? It's just 1. Another way of seeing this is they could have canceled here and you just get x. And of course, something I missed here is I didn't take log of both sides. There we go. Or else we would have got 16, which is incorrect. So you want to take log whatever the basis of both sides of the equation. So that's what I meant to do here. So now log base 4 of 16, well, if you write this as 4 to the 2, bring the 2 out, and you get log base 4 of 4, which is just 1, so they cancel out. So right away you get x is equal to 2. Which seems a little more roundabout because we still had to write 16 equals 4 to the 2 anyways. So this is definitely the more direct way of doing it. I want to show you another way, and it involves using ln's. Now, ln may seem kind of weird. Why are we using ln? Why not just use log base 4? Well, like I said in the previous section, I like ln, so I'm just going to obviously use ln whenever I have a chance. Also, ln is the natural logarithm. In fact, it doesn't really matter which log you use because of the change of base formula. So I'm just going to use ln because it's shorter to write, only 2 letters instead of 3. So if we take ln of both sides, we can say ln of 4 to the x is equal to ln of 16. Okay, so far it kind of looks the same. Now, of course, what I'm going to do, yes, I'm going to write 16 as 4 to the 2. All right, then I'm going to bring the powers down. So this is x times ln of 4 equals 2 times ln of 4. And when you divide by ln of 4, you right away get x is equal to 2. So you still get this, and I made it look shorter, but it's kind of the same thing, really. I'm just showing you different ways. Moving on, let's get to this one. So here, this is kind of similar to the previous one in the sense that it involves a one-to-one property. So if you just add ln of 2 to the other side naturally, you get ln of x is equal to ln of 2. And then the one-to-one property, just like here we use one-to-one, but for exponents. Here, one-to-one for logarithms tells us that x is equal to 2. So we also get x is equal to 2 coincidentally. But yeah, that's one way of solving this. Another way of solving this, notice here we took log of both sides. Here we can take both sides as powers of whatever base we want. Believe it or not, that's actually a procedure you can do. It's an operation you can do to both sides of an equation. So what we can do here is look at our original equation and take, well, the base here, remember ln is log base e, so we could take both sides as powers of e. So another way of handling this is we can say e to the left side is equal to e to the right side. This may seem kind of weird, but again, there are multiple ways of continuing. I guess we can say on this side it splits. So we can say this is e to the ln of x times e to the, I guess we could do divided by because we're subtracting powers. There's so many ways of doing this, honestly, but yeah, let me just do that. So let's say divided by ln, e to the ln of 2. E to the 0 is, of course, 1. And e to the ln, if you don't remember, cancel each other out. So we get x over 2 is equal to 1. And then finally dividing both sides by, or multiplying both sides, I should say, by 2 gives us our result. And again, there are a bunch of other weird ways you could do this. You can use the quotient rule of logarithms here to write this power as ln to the x over 2. The e and ln's cancel, and right away you get x over 2 equals e to the 0, which is 1. So there's all sorts of funny ways of handling this. Let me kind of separate things here. This one, I'm not going to do anything super crazy. I can just write this in logarithmic form. So what's the base? It's e. So log base e is ln of what equals what? So let me make more space. Well, remember that log solve for powers, the power is x. The other number we haven't used is 2. So x is ln of 2. That's the answer. If we wanted to do this another way, we can take ln of both sides. And when you take ln of both sides, you'll have ln of this equals ln of that. E and ln's cancel, yeah, we get x is equal to ln of 2. So sometimes doing that actually makes things pretty quick, but they're basically equivalent. It just kind of depends if you like remembering how those three things move around as far as converting between exponential and logarithmic forms, like I've kind of been building everyone up to. So in my opinion, that is probably the better way of going about it. It's a lot quicker if you get used to converting. But to be quite honest, no one's going to remember that in the long run. And what people tend to remember in the long run are that you can take both sides as powers of a base, like we did here, and you can take ln of both sides. And those techniques you'll see a lot later on in other classes, like calculus courses, for instance. That technique is used all the time. Just because at that point, people often forget about how you convert between logarithmic and exponential forms to more sophisticated, kind of mature way of handling it. But I'm okay with us converting between the forms because I think that's better suited for this class. But I'm just, speaking my mind. So with that being said, let's just do it that way here. Let's convert this to exponential. The base is 4, the power is 3 because log solve for powers. And right away we get x is equal to 4 to the third, which is 64. So now I'm going to try to summarize some of these strategies and then we'll move on and do some more complicated examples. So these are the strategies I was talking about earlier on how to solve certain logarithmic and exponential equations, and obviously I have a lot to say. First off, if you take your time to read these, they're very, very similar. I'm going to go through them, of course. So they're each 3 steps. For a logarithm, let's just start with logarithms first. So here I say use logarithm properties to write equation in logarithmic form. So if it's a logarithm equation, you'll right away you can tell because either it'll be an ln or log base, whatever. And then you can simplify it using logarithmic properties to write it as a log of something equals a number, log base something of something equals a number. That's logarithmic form. Then step 2, convert this to exponential form, and you may need a calculator because let's say for instance it's like e to the 3 and you want to compute that. You can use your calculator to round, or you can leave it in that funky exact form if you like. It kind of depends. And finally, I say here, step 3, check, and I say it's not optional. It kind of is optional if you're very clever about it and you're certain with your math, but for the most part, you want to check. Now, let me say here that if you're clever about it, one way to be clever about it is to check for negatives. So check for negatives on the inside, for log of a negative. Because log of a negative means there's an extraneous solution. Now I'm going all over the place with this. But let me just kind of box this in here for that. So check to see if you have a log, whatever the log is of a negative number, because that means there's an extraneous solution. And you can of course do this just by plugging it in to see what the insides amount to in the original equation. So when you check, you can just really do that. But it's not a bad idea to just check completely just to be sure. And I say here, there's also an alternative you can do. Instead of following these steps, you can take both sides as powers of an appropriate base, apply exponent properties, and then simplify and finally solve. Now moving on to exponential equations, and we see the exact same thing. So we want to use exponent properties to write in exponential form some base to some power equals a number. Step 2, convert this to logarithmic form and simplify. Here you may need to use change of base formula along with your calculator. Here I say change of base formula because, of course, let's say you have, 3x equals log base 4 of 5, and you don't know what log base 4 of 5 is because it's not an integer. You can use your calculator with change of base, write it as ln of 5 or ln of 4, or log of 5 or log of 4, whatever you choose. And then you can approximate and then divide to solve for x. And finally, step 3 here, you can check your solution. Here it is optional. Why is it optional here? It's because the domain of exponentials is negative infinity to infinity. Any real number works. So there's no domain issues we have, so you don't have to go back and check. If you recall from the previous types of problems that we've solved, equations that we've solved in the past, that is, the only real time we had to check is when there was a domain issue. And the domain issue really only occurred when you have a function that has a domain that's not all real numbers. So if you think of radicals, that's a good example. Denominator is also a good example. The denominator can't be 0. With radicals, you can't have a negative inside of an even index radical. For logarithms, it can't be negatives on the inside. But exponents, you can take anything to any power. Any number to any power works. So it's kind of optional here. The alternative I discuss here is you can take an appropriate log of both sides. So you can use a log or ln, those always work. But if you notice your base is like 5 throughout, you can just take log base 5 of both sides, and that's fine. Then apply log property, simplify and solve, and that's it. So these are the ways that we'll be solving these equations. I'm not going to do the alternative way so much, but when we don't have a choice, and we'll kind of see what I mean by that in a few of the examples, I'll mention that I'm doing it the alternative way. But aside from that, though, I'm going to try to stick with these 3 steps for each of these. So let's take a look and see how crazy it gets. All right, so for this first example here, this is, of course, an exponential equation. So we're going to write it in exponential form by dividing by 8. And in doing so, what we get is 10 to the 3x is equal to 12 over 8 reduces by dividing by 4 to 3 over 2. This, of course, is step 1 from the previous procedure we spoke of. This is an exponential form, so now let's convert it in step 2 to logarithmic form. So this is log base, what's the base? 10. Remember, log base 10 is the common log, so we don't need to write the base. Of the inside is what the exponential is equal to, so 3 over 2, equals the power, because log solve for powers, 3x. Now, finally solving, so that's step 3 is just solving. Divide by 3, I'm going to write it like this. X is equal to 1/3 log of 3 over 2. Now, if you want to approximate this, I got about 0.059 when rounding to 3 decimal places. I like leaving it in an exact form, though, but it depends on what you're asked. If you're asked to round, then round. If you're asked to leave it in an exact form, well, then just leave it like this. Okay. Here for this next example, this is a logarithmic equation because ln is involved, of course. The base is e. Remember, ln is log base e. And we can alternatively to the procedure we spoke of earlier, the alternative is to take both sides as powers of that base. So we can write this as e to this side equals e to that side and then go from there. But I'm going to stick with what I said earlier, and I'm going to apply the procedure when we can, and here we can. So I want to use log properties to write this in logarithmic form. And the property applied here, of course, is the quotient rule, because it's a log of this minus log of that. So we're naturally going to write this as log of the first one over the second one equals 2. Remember, ln means log base e, so I'm just going to write that just so it's easier for us to convert. Converting this to exponential now, so this is step 1, writing it in logarithmic form using log properties. Step 2 is converting to the other form, which in this case is exponential. So that's the base e to the power 2 is equal to the inside, which is x over x plus 1. There are so many different ways of solving this, but I'm just going to do it like this. So I'm going to write e squared is just a number. Okay, So we have a number equals x over x plus 1. If you cross multiply or just multiply this denominator to that side, you'll get this. E squared times the quantity x plus 1 is equal to x. Believe it or not, this is just a linear equation now. If you distribute this e squared, which again is just a number, into this, then you can solve for x by moving things around. It looks a little funny, but just bear with me. And let's see if we can follow. So we get e squared x plus e squared equals x. I want to move all x's on one side and all non-x's on the other. So I'm going to subtract this x term to this side to combine with that x term. So let me just do that actually. So we have e squared equals x minus e squared x. Now I'm going to notice they both have x in common. So if you factor it out, you get e squared is equal to 1 minus e squared all times x. Of course, if you distribute this x back in, you'll see that this indeed makes sense. And then finally, dividing both sides by 1 minus e squared gives us our answer. So we get x equals e squared over 1 minus e squared. And if you want to approximate this using your calculator, you certainly can. So just kind of be careful how you plug this into your calculator. Remember the bottom has to be all in parentheses because it's one denominator. And I got negative 1.156. I'm not sure if that rounds. It does round. It rounds to 157. So that's one way of rounding this. But before moving on, there's something that doesn't feel right about this. Remember, for exponential equations, you don't necessarily have to check, but you can. For logarithmic equations, it's not an option. You have to check. Why is that? Because you cannot have a negative inside of the logarithm. Notice here, both of these are bad when you plug in this, this solution. Why? Because it's negative 1.1 something. Adding it to 1 is still leaving a negative, and leaving it alone, of course, is still negative. So this actually is an extraneous solution, believe it or not. So since it's extraneous, what does that mean? Well, that tells us that actually that I shouldn't have really boxed this. I really should have boxed no solution. So in actuality, there is no solution. Now, it wasn't obvious that it was negative before approximating it. So approximating with a calculator is not a bad idea. You can kind of tell e squared is positive because e is positive. E is bigger than 1, it's 2 point something. That to the second is even larger. And 1 minus that is going to be negative, so it's positive over negative, which is negative. So there are ways of telling, but of course approximating with your calculator I think is never a bad idea. Just keep in mind sometimes you will be requested to write in exact form. So don't always approximate and just do that all the time, but you know, it's something that you can take advantage of sometimes. Like this was a good example of that, I think. I want to do 2 more examples that are a little more challenging in my opinion, so let's take a look right now. Okay, so to be quite honest, both of these are a little crazy, but let's see if we can take a look. Now, for this one, I'm going to try to stick with our procedure. For this one, I don't think we can. Well, there's kind of a way of doing it, but it's not really worth it, to be honest. So here, what I'm going to do is I'm going to move everything to one side, so that we have all logs on one side. I'm going to condense them into one log to write it in logarithmic form. So to move these to this side, I have ln of x plus 5 minus ln of x minus 1 plus ln of x plus 1 equals 0. And in retrospect, maybe I should have just subtracted this to that side, but that's fine. Now we can combine these as one as, well, let's see if we remember how to do this. So to condense into one logarithm, since there are no numbers in front, we don't have to bring in anything as powers, but whatever is positive we'll say on top of the fraction, so that's x plus 5 and x plus 1, and whatever has a minus in front, because of the quotient rule, will be on the bottom. So that's our x minus 1. Of course, equals 0, and now we can write this in exponential form. The base here is e, so this is e to the power 0, because log solve for powers, again, equals this mess. Well, here's what I'm going to do. I'm going to FOIL the top just real quickly. So I'll get x squared plus 6x plus 5 over x minus 1. E to the 0 is just 1. So really all we need to do now is cross multiply, move everything to one side because it's quadratic, factor and solve. So again, I may run out of space, but let's see. So if you cross multiply, this multiplied to that side is just x minus 1 times 1 is just x minus 1 equals this. Subtract these to this side, so let me do it like this. So minus x plus 1. We get 0 is equal to x squared plus 5x plus 6. This does factors as x plus 3 and x plus 2. I want to say, yeah, it seems to work out. Now using the zero factor property, we get x is equal to either negative 3 or negative 2. We have to be careful because these are negative numbers and you can't have a negative inside of the logarithm. This does not necessarily mean that they're both bad. We have to plug in and see if we get negatives. Now, when you plug in negative 3, negative 3 plus 5 is positive 2. So that's okay, but it needs to work for all of them. Negative 3 minus 1 is negative, it's out. And actually, negative 2 minus 1 is also negative, so that's also out. So unfortunately here, there are actually no solutions, kind of like we saw in the previous problem. So that's kind of unfortunate. Let me write like a sad face there. Makes me a little sad because we did a lot of work, but at least we saw the work there. So it's possible that you see a problem like this on an exam or something, and you check and they're not negative, so you get the right answer. Anyways, so sometimes you have no solution, they're both extraneous, but regardless, we did the work and we got our answer. Now on to this one. This one, I may need a little more space. Just to be safe, let me erase this and move this up and move on. All right, so here it is shifted up. And yes, we cannot apply the procedure that I spoke of previously for exponentials because to write this in exponential form is kind of difficult unless you just pick a side and go with it. Like if this was the base 3 and then you write it in logarithmic form as log base 3 of this equals that power. You can kind of do that, but I think a more elegant way of doing this is just taking log base, whatever base of both sides. Since I can't decide which one I like better, I'm just going to use what I like, ln. So I'm going to take ln of both sides and let's see what happens. Now, the only reason why you like to get logarithms involved is to use the power rule. Maybe I'm biased because like I've been saying, if you haven't noticed already, I like ln's and I like the power rule. So if you apply ln to both sides and then use the power rule to bring these powers out, like this, we get 2x minus 5 multiplied by ln of 3 equals 3x plus 1 multiplied by ln of 5. Now it's up to you. If you want to approximate, that's fine. I guess it depends on what the problem says, of course. But ln of 3 and ln of 5, much like we saw with e squared in the previous example, are just numbers. So I'm going to treat them as such, distribute, move things around and solve for x, and hopefully you can follow. So let's see. So we get ln of 3 times 2, so it's just 2 ln 3, x, minus 5 ln 3, equals 3 ln 5 times x, plus ln of 5. I hope you don't mind I'm not writing the parentheses for ln's here. I want to move all x's to one side and all non-x's to the other. So let's see. I'm going to keep this x on this side, so that's 2 ln 3 times x. And this x I'm going to subtract to this side, so minus 3 ln of 5 times x. This term that does not involve x, I'm going to add to this side. So I'm going to get ln of 5, that guy, plus 5 ln of 3. So just to understand what I'm doing here, I'm double underlining everything and move to the left, and single underlining everything that I keep on the right and move to the right. Good. So now what? Well, these both have x's in common, so pull it out. So we have 2 ln of 3 minus 3 ln of 5 all times x equals ln of 5 plus 5 ln of 3. And divide both sides by 2 ln of 3 minus 3 ln of 5 Yikes. Looks like a lot. And it is a lot. Finally. So, my pen's even running out of ink. So, a lot of solving we've been doing. So we get x is just equal to this, so I'll box this. It is not necessary to check just because it is an exponential. But if you want to approximate, that's fine. In fact, I'll approximate for you. Let's see what we get. Now again, be very careful on how you plug this into your calculator, but here's what I got. I got negative 2.699 after rounding to 3 decimal places. Now if you didn't get this, make sure you plug things in correctly because I'm fairly certain this is the answer. Now again, we could plug it back into the original and check. I'm not going to do that, but you can try and you can see that this indeed does work. There's one more thing I want to show though. It's not another example, but it's another way of writing this solution here. So believe it or not, we can actually apply a lot of logarithm properties to condense this into one logarithm. It's pretty cool. It's maybe not worth it, but I want to show you. So let's see if we can take a look. All right, so this is the answer we just came up with. And now what I'm going to do is I'm going to combine the top and bottom separately using log properties, mainly using the rules we saw in 5.3. So that is the power rule, quotient rule, and product rules. And let's just get started and see what happens. So for the top, we get ln of 5 plus ln of 3 to the 5th, like this. On the bottom, this 2 and 3 on the outside get brought in as powers. So this is ln of 3 squared minus ln of 5 to the 3rd. So just to compute what these things are, this is ln of 5 plus ln of 3 to the 5th is 243. ln of 3 squared, that's 9. ln of 5 to the 3rd, that's ln of 125. So now on top, we're going to use the product rule because, of course, it's addition. So that's ln of 5 times 243 over ln of, well, this is going to be the quotient rule because it's subtraction. So it's going to be ln of 9 over 125. Okay, now what? Well, multiplying 243 to 5, I believe that is going to be 1215. So ln of 1215. And you can check me on that, but really what I'm doing is 5 times 24 is 120. So 5 times 24 with a 0 is 1200. And then 5 times 3 is 15. So 1200 plus 15 is 15. But in any event, you can use your calculator and you get that. On the bottom, this doesn't reduce, so I'm just going to leave it like that. And you'd think I'd be done because there's not really much more we can do to simplify this. But you actually kind of can. You can use a change of base formula in reverse to finally get x equal to log base the bottom inside 9 over 125 of 1215. Crazy. So yes, this is something that you definitely can do. You can actually get any expression involving logs, in this case one that looks like this, and write it compactly into one nice logarithm. It's a weird base though, and the practicality of doing this isn't the best. In fact, if you wanted to use your calculator to evaluate this, you'd probably have to do this anyways, change a base. So maybe the most simplified version would be this on top. And to be quite honest, I don't really expect anyone to really use this method. It's just something cool I wanted to show to end 5.4. Now, this ends chapter 5, and it really ends our discussion on Algebra 1 in general. So now we're going to move on to Algebra 2. In the next videos, it's going to be a lot of crazy cool new things I'll be showing you guys. And the Algebra 2 that I'll be lecturing on will involve trigonometry, and we'll get into systems of equations. And it's going to be kind of crazy. In fact, some of you may think, well, trigonometry is a different class on its own. But the way I'm going to handle Algebra 2 is I want to introduce that. So it's really more of a pre-calculus course than a pure algebra course. But in any event, that's how I'm mixing things in there. So yeah, it'll be a lot of fun. I'll see you in the next videos. As always, thanks for watching. See you then.